But yeah.
So if we're creating a game, we can make reasonable predictions about where script overhead is most likely to be a problem and lean toward C++ in those areas. That might include all sorts of low-level systems, anything that manipulates data on a large scale, anything that does lots of work in tight loops, and anything that scales to a large number of actors.
Yes, this is good. So this is why I always get annoyed when friends that do C++ or people that kind of just think like you should start like, yeah, I have a friend that I worked with that is using C++, and what he wants to use C++ for is like setting up classes. Like before we create any class, we kind of create it in C++ and maybe like initialize like variables or something. But to me, it seems like that's kind of the worst use of C++. It'll just make things longer, and I can do all of that stuff in blueprints, and it's not like performance intensive. It doesn't do anything. Like I think C++ is the best when we just farm out blueprints. We just get a bunch of stuff done in blueprints, and then we see, okay, do we have big arrays that we need to go through frequently? Sure. Okay, C++. Do we have some iterations? We need to run something like 100 times on a tick, and we have a bunch of casts. Okay, sure, C++. So you kind of just grab whatever needs to be heavily optimized, because if you do it in blueprints, you literally lose like 10, 20, 30% of frames or something. Bam, put it to C++, done. So I think, yeah, that's kind of the best use, not just instantiating stuff, or not just going with C++ right away and then spending like 5 times more implementing features because you have to compile, reset your engine a lot, deal with random small bugs for hours. So I think, yeah, blueprints do give you that speed and flexibility, and then you just pick out few parts where it's very performance heavy, put that to C++, and you are good.
But if you find yourself weighing performance trade-offs, remember that the 80-20 rule applies to software optimization. 80% of execution time is spent running 20% of the code. You can use a profiler to see where every millisecond of the frame is going, and your decisions about what to use a profiler.
Oh yeah, profiler. You can. There is some other. I need to do like a dedicated stream or something where we go over our different ways to like debug and profile blueprints. There's some good stuff. I'm not sure if it's profiler, but I think there is some new stuff where you can basically run debug on a blueprint and basically see exactly each function, each thing, how long it took, and it kind of shows a hierarchy of like the longest executing functions and stuff like that. And you can use that to just get that info, and you know exactly, okay, this, and this, we need to optimize C++ or optimize in blueprints.
Profiler to see where every millisecond of the frame is going, and your decisions about what to optimize should be informed by that data. If you have a system that's implemented in blueprints and you spend a week rewriting the whole thing in C++ to realize a 20-fold performance increase, but the original blueprint system only used up a tiny portion of your overall CPU budget.
Yeah. So yeah, this is annoying, yeah. Where that's why don't start with C++ right away, because you're just gonna waste more time for almost no performance. But if you actually know what actually hits performance, which you will know when you create a bunch of stuff with blueprints, you're going to realize, okay, I just can't do for loop with a bunch of like cast or something. Like even if I have to, I just can't. So C++. And then you're going to save from like 20 millisecond delay, you're going to save like, I don't know, put it to like 1 or 2 milliseconds. Like if you make like there is some optimizations in blueprints that you can also do, but yeah, this is kind of a thing where you have to learn blueprints so you know if it's even optimizable instead of spending much of time optimizing in blueprints. And maybe it's just not possible. Some things are just not possible in blueprints. So it's good to know how you can optimize things in blueprints so you know if you should or should not, or you should go to C++.
Then you haven't really accomplished much. Or maybe the original implementation did take up a hefty portion of the frame, but you could have achieved the same savings by simply rewriting a single function in C++ instead of the whole system. So C++...
Yeah, or even just setting that one function to thread safe, and you just did like insane optimization in blueprints because everyone has like 8+ cores on their CPU.
...is faster, but whether that speed difference is significant depends on context. And if there's any doubt, you should measure performance with a profiler and make decisions based on that data. But of course, there are reasons beyond just execution speed that you might want to write some part of a system in C++. So let's dive into those. Game programming involves more than just writing function implementations. With an object-oriented framework like Unreal's, you're usually writing those functions as part of a class. So before you start implementing a class's functions, you need to define the class in the first place. Defining a class means establishing what it should be responsible for, and then figuring out what properties and functions it needs in order to handle precisely that responsibility, no more and no less. It also involves figuring out which of those properties and functions should be visible to other code as part of the class's public interface, and which can be hidden away as private implementation details. In C++, your class definition is written in a header file, while your functions implementations are typically written in a CPP file. A blueprint asset is roughly equivalent to both of these files. The blueprint's parent class, along with its list of components, properties, and functions, form the class definition. The event graphs and other function graphs, as we've already seen, contain the function implementations. At this level, C++ and blueprints are roughly equivalent in terms of how they allow you to define and implement new classes and other types. The difference arises when we start talking about dependencies between types. Every time you create a class, or a struct, or an enumeration, whether in C++ or in the editor, you're defining a new type. At any point where one type needs to know something about a different type, that's a dependency.
Is it called polymorphism? That's what he's talking about? Like in blueprints, you can't have like multi-parent class, I don't think. Yeah, I'm not sure what he means. Okay, let's continue.
In your codebase. Wherever possible, it's best to make sure that dependencies are only one way. For example, if you have a weapon that fires a missile, that implies a one-way dependency. The weapon has to know about the missile in order to spawn it, but the missile doesn't have to know anything about the weapon that fired it. Now let's say the weapon is only allowed to have one missile in flight at any given time. We have to wait until the existing missile explodes before we can fire a new one.
Okay.
We could implement that behavior by having the missile call a function on the weapon to let it know that it can fire again.
But then you have to create a dependency. So missile depends on the character. Is that right?
But that would complicate our design by creating a two-way dependency for no good reason.
I mean, then you could create like a delegate on the missile that you attach an event to.
The missile shouldn't have to know anything about the rules that govern the weapon. Whether the weapon should be able to fire is the weapon's concern. The missile's only job is to explode. So to keep this dependency one way, we can instead give the missile a delegate that's fired when it explodes. In blueprints, delegates are also known as event dispatchers. The missile only has to fire the delegate without caring what happens as a result, and the weapon can bind a callback to that delegate to update its own internal state.
Okay.
This way, the weapon and the missiles stay out of each other's business.
Okay, so he said that like the difference is that the delegates, it sounded like he's gonna say like the dependencies are the reason why you should do C++. I'm not sure what he means here. Probably gonna show it.
And we keep the shared surface area between the two classes as small as possible. As a project grows bigger and more complex, it becomes more and more important to manage these dependencies, to make sure that the boundaries between different parts of the codebase are clearly defined. One way of accomplishing that separation in C++ is to use modules. You typically have a single primary game module that contains the core gameplay classes, like the game mode, player controller, and pawn. As your project grows in complexity, you might split off different features and systems into their own separate modules. In order for a class in one module to reference a class in another module, there needs to be an explicit dependency between the two modules, and the class or function being referenced needs to be exported as part of the module's public API. Since module dependencies should generally always be strictly one way, this leads to a sort of layered architecture. In this example, our weapons module sits below our core game module. So we could have our pawn spawn a weapon, and the pawn could call functions and access data from the weapon class. But the weapon would never be allowed to know anything about the pawn class. That's a restriction that we're imposing on ourselves. We're saying that by design, the types in the weapons module should never depend on the types in the core module.
Makes sense.
If we try to write code that violates that established design, then the build system won't allow it. We'll get a linker error that indicates we're trying to use code from a module that's not an explicit dependency. While we might be tempted to just create that new dependency, this is usually a sign that we need to think more carefully about what we're doing and either change our code to better suit the established design or else reevaluate those initial design constraints. There are a number of concrete benefits to the prudent use of modules. It keeps build times under control.
So with game features, I think you can do this similar thing without using C++. I was doing this with the Pyric game. I'm not sure if that's the exact thing, but basically you can create like game feature plugins that kind of just can hold whatever thing you want to hold, like one type, one thing, one feature, and then you can basically tell it which dependencies it has, and that way you don't have any callbacks or any dependencies that you don't want. And then they can reference the blueprints inside one game feature plugin can only reference thing that he's dependent on, and in the content, your main content folder or whatever stuff is in your main project. I think you can now this video is made like 2 years ago, I think, so I'm not sure if the game feature plugin was created, and so I'm not sure. But yeah, I think you can do this in blueprints now, so maybe this isn't even a concern anymore.
Within a team, it makes it easier to establish which team members have ownership over different parts of the codebase. And in theory, it lightens your cognitive load. If you're doing work inside of a single module, then you can safely forget about all the code and all the other modules, except where you need to bring in explicit, deliberate dependencies. Of course, module boundaries are a double-edged sword. The key benefit of splitting your codebase into separate modules is that it forces you to think about your design when you add new types or dependencies. The key drawback of splitting your codebase into separate modules is that it forces you to think about your design when you add new types or dependencies. But when modules are used wisely, they're a great tool for keeping larger projects organized. The overarching design of your project's codebase can be writ large in your module boundaries, and you can be confident that if your project successfully builds from source, then those boundaries are not being violated. There are no such boundaries in blueprints. You can think of all the blueprints in your project as forming a single conceptual module that sits above every actual C++ module. Any blueprint that you create can freely reference any type declared in any source module, so long as it's a blueprint type. For high-level in-editor scripting work, it's hard to imagine.
Yeah, for modules, this might be true. The only issue is that now you have the game feature plugin that, how I understand it works is, you have your quote-unquote plugins that effectively work like modules, like you have dependencies, you have all of that. So if you have your plugins, let's say it works like this, and then you have a then let's say you have a game feature plugin here that references something like this. If you have a blueprint in here, it's going to be able to reference all of this, but if you have a blueprint in here, it's going to only be able to reference stuff from here. So I'm not sure if this applies with game feature plugin.
Imagine these sorts of boundaries being anything but an unnecessary hindrance. So this isn't much of a downside.
Maybe we can.
But if you're writing core game systems in blueprints, it's no less important than in C++ that you establish a good design with a clear separation of concerns. And with fewer tools to enforce the boundaries dictated by your design, you may have to be a little...
What if he... Oh my god, I commented, I didn't even finish this section. What if he says now, and actually, game feature plugin does...
more vigilant to keep your blueprint codebase from becoming too tightly coupled. Blueprints are assets, so how you organize your blueprints is a matter of asset organization, which varies by project and by team. It's worth pointing out that you can use the editor's reference viewer to get some very useful at-a-glance information about the dependencies between your blueprint types. So,
yeah, there are some inner dependencies to blueprints, but yeah, I guess separating stuff into plugins before was a bit more annoying, but with game feature plugins, I think it's better, but yeah.
So module boundaries aren't a thing in blueprints, and splitting your project's C++ source into multiple modules is entirely optional. But it's still important to be aware that there's a conceptual module boundary between C++ and blueprints, and it forms a one-way dependency. Your blueprint types can depend on C++ types, but your C++ types can't know anything about blueprint types. Let's say we've been working purely in Blueprint.
That is true, because blueprints are kind of created on top of C++. C++ already compiles and does any stuff without knowing about blueprints. There might be some way that you could create some dependency, but yeah, that would be hard.
We have a custom pawn class and a weapon class. There's a simple one-way interaction that we need to facilitate between these two classes. The pawn spawns a weapon on begin play, and if the player presses the fire button, then the pawn calls the fire function on the weapon. We have our weapon blueprint set up so that when we fire, we run a line trace and then spawn some particle effects. Now suppose we want to start refactoring some of our core classes into C++, and we start with the pawn. If we move our pawn class into C++ but leave our weapon class defined in blueprints, then we have to contend with the fact that at the level of our C++ module, weapons don't exist yet. We can still spawn a weapon thanks to Unreal's reflection system. Any UObject class, regardless of where it's defined, has a UClass object associated with it. And as long as we can get a reference to the weapon's UClass, we can spawn an actor of that class. Here we've given our pawn two properties. One is the class that we want to spawn an instance of, and the other will hold a reference to that actor itself. In our constructor, we can resolve a reference to the class that's generated from our weapon blueprint. Directly referencing a blueprint asset from C++ like this is a somewhat brittle approach, but we'll see some alternatives in a minute.
Oh yeah, this can get rough where you have a direct reference. Okay.
For now, we initialize our weapon class
This can kind of break by just you moving around blueprints.
Property to hold a reference to our blueprint generated class. Then in begin play, we can spawn an instance of that class. But notice, our weapon property's type is just actor. The weapon type is defined in blueprints, so our C++ pawn has no notion of what a weapon is, other than the fact that it's some kind of actor. That means we can't call the weapon's fire function, since that function is defined in a blueprint.
Oh yeah, so what can he even cast? If he can't cast, what can he do then?
We could technically look up the function by name and invoke it dynamically, but that would be a pretty questionable thing to do, to say the least.
Yeah, that's not good.
But technically, if we delete our blueprint pawn and switch over to using our new C++ pawn class, everything still works. The real solution is to properly refactor our weapon class into C++. But our weapon, as we've currently implemented it, spawns particle effects too. That's not something that our C++ pawn implementation really needs to care about, and we'd prefer to keep those cosmetic effects implemented in blueprints. So we end up with a base weapon class defined in C++.
Oh, and then he's gonna have to trigger the parent, or what is it called? Yeah, add parent event, and then he's gonna have to additionally add this, I think, in blueprints.
And we further specialize that class with a weapon blueprint. In our C++ weapon class, we implement the functionality that's relevant at this level, basically just the fire function, along with whatever other data or helper functions it needs. Then we can make a few changes to our pawn. We now have a weapon class defined in C++, so we can use that specialized type instead of actor. We also want to make the weapon class property editable, so it can be overridden in blueprints. In the CPP file, we no longer need to reference the blueprint directly. As a default value, we'll just initialize weapon class to our base C++ a weapon class. The spawning is no different, except that we now know a more precise type for the resulting actor. And finally, in our input binding, we can just call the fire function normally. We now have a working C++ implementation that gives us a fireable weapon by way of the pawn. But that's just the essential functionality, with no visual feedback for the player. So how do we bring our original mesh and particle effects back in?
So complicated, would have done it 5 minutes ago in blueprints, okay?
The answer is to reparent our original blueprint to the new C++ weapon class.
Yeah, I'm really interested. I should maybe do a test or something. Create a simple project and see... This is a little bit unrelated to whatever he's talking about now, but I just remember maybe it would be fun to just see how much nativization helps blueprints. So I have some like blueprint heavy project, export it, and then see the difference between like editor and like the exported project. See like the frame rate, the hiccups. I feel like there will be like 30% difference in like FPS.
Which will give us a chance to look at basic interop between a C++ base class and a blueprint subclass. But before we do that, let's look at an alternative approach that keeps everything in C++. For just a moment, let's convince ourselves that real programmers do everything in C++. We don't want to sully ourselves with blueprints because we're real programmers. Okay, so we need to add a mesh component to our C++ weapon class, and we need to store a reference to the particle system asset for our muzzle flash. In the constructor, we need to get references to the assets for our weapon. We can use a static object finder to ensure that this asset lookup only happens once when the game first boots up. For each asset, we'll need to paste in its exact path, which we can get by locating the asset in the content.
Oh my god, it's so annoying when there is like a direct. Like, I don't know if, what is it called, like a redirector, if you clean up redirectors, if that helps, but in C++, but I think like every time now, if he wants to change the location of his meshes or whatever, particles, he's just gonna have to go to C++ and fix the locations, which is really annoying.
Browser and choosing copy reference. So now we have our asset references hard-coded directly into our source. There are some cases where this is fine, particularly for editor-only asset references or for plugin or engine-level functionality where a specific asset really is integral. But for game objects like this, hard-coded asset references are typically best avoided. For one, this approach creates a hard reference between our C++ weapon class and any assets it uses.
Hell yeah.
This means that as soon as our game starts up and registers the weapon class, it immediately has to load those assets, and those assets stay in memory permanently.
Wait, is that true? So just because that class exists, that means this is all gonna be loaded even if you don't even load the weapon? Is that what he's saying?
Any assets it uses. This means that as soon as our game starts up and registers the weapon class, it immediately has to load those assets.
Oh, okay. This is, I guess, the same for blueprints. I thought he was talking about like just loading the game, but he's saying when you load the weapon, these assets are gonna be loaded, which is kind of like how blueprints work if you're not using like soft object references or soft class references.
And those assets stay in memory permanently. But also, this is just a questionable choice in terms of how we're organizing our project. The question of which assets we're using is a very high-level concern, and our base C++ class is designed to handle slightly lower-level functionality. If we make our C++ class responsible for handling assets and cosmetic effects, in addition to the job it already has, we may be giving it too many responsibilities and muddying our design. If we handle assets in blueprints, then we get a much more natural user experience with immediate visual feedback for tweaking and fine-tuning, and our asset references are managed for us in a way that allows assets to be streamed in and out, and we end up with a cleaner design, where the logic that dictates our actor's look and feel is separate from the logic that dictates its direct impact on the game world.
To be honest, this is fine, the distinction he's making. The only issue is that you could, for all of this right now, you could do both in blueprints, and I would then follow his original statement about performance, where you do all of this in blueprints and then see, okay, our collision queries are too expensive in blueprints, let's move this to C++ or something like that. But if everything works fine in blueprints, then you just leave it in blueprints. Because all of this can be technically done in blueprints, even if this is kind of a lower level thing. It's not expensive, it's not crazy.